In this video, I'm going to show you why we need to use implicit differentiation and then how to use it to find the derivative. So far, all the functions that we have been differentiating have been expressed in the form y equals f of x, where y is said to be defined explicitly in terms of x, because y appears alone on one side of the equation. So if you take a look at this equation here, we can see that y is on the left side, but the x appears on the right side on its own. Now consider the Folium of Descartes. It's given by this equation here, and this is what the graph looks like. We can see that the graph consists of all the points x and y which satisfy the equation, such as 0, 0. We can see that's one of the points, and when we plug it into the equation, left side equals the right side. However, notice that the graph is not the graph of a function, because if I draw a vertical line anywhere here, it's going to hit the y value, or two different y values for the same x value. So moreover, it's actually very difficult to solve for y, as you can see, because we have y on the left side and the right side, unless you happen to know some cubic formula. Now, if we take small pieces of the graph, such as maybe over here or over here, they do look like functions because there's nowhere for me when it does pass the vertical line test. Now, we just have to be careful that we don't pick too large of an area. So for such a piece, the equation defines a function, y equals f of x, implicitly. Now, implicitly means that y may not be isolated in terms of x, but a given x still produces a unique y value. Now, if you look at these places here, we can still say that x will give us a particular y. Now, I like to think of it implicitly as opposed to explicitly. If you have x and y on one side and the other side, and you can't really separate them, then that would be implicit. Whereas y is isolated on the left or the right side, then this would be explicit. Okay. Now, the idea is to differentiate the equation as it is, so we can't isolate the y, but we need to use the chain rule to do this as well. So when you differentiate, this actually might produce another equation from which you can get y prime, but it might be still expressed implicitly. So let's take a look at differentiating the Folium of Descartes. And I will show you how to do this term by term with respect to x. So we're first going to take the derivative of x cubed. Now with respect to x, so that part is quite simple, it's the same as what we've done before. So the derivative of x cubed is 3x squared. Okay, so far we have 3x squared plus. Now the derivative of y cubed with respect to y would be 3y squared. But you're differentiating with respect to x, so you need to use the chain rule. So differentiate the cubing function, which means that we're going to hold the inner thing, that y part, fixed. Then we're going to differentiate the inner thing, which is the y. Okay, so remember so if we think about it like that, we still have the beginning part, 3x squared. We also have 3y squared, which would be the outer part. Okay, so we would consider 3 the outer part. Now we're going to differentiate the y. So to say that we're finding the derivative of y means that we would find dy dx. So we need to place that part into our equation. Okay, that equals, I'm going to just put dot, dot, dot. So I'm going to do this step by step. So now we're going to differentiate the right side, the 3 times x times y. So the 3 is constant, so we can kind of ignore that part. But the x and the y is a product, so you need to use the product rule. Now remember, however, that the derivative of the second factor y is going to be dy dx, because remember, we're differentiating with respect to x. Okay, so how does this work? So I'm going to rewrite the first part. Now you wouldn't have to do this step by step, but I'm just explaining it. So that's why I'm doing all of this step by step. All right, so we have 3, which is just the constant, and the derivative of x is 1. So we have 3 times 1, and we're going to leave the second part. When we use the product rule, we're going to leave that the same. So it'll be 3 times 1 times y plus 3. Now we're going to leave the first part alone, which is x. So 3 times x. And now we're going to take the derivative of y. Now y, remember, is with respect to x. So this is going to be times dy dx. Now dy dx represents a derivative. So I want to solve this equation here for dy dx. So I'm going to move all the terms that don't have a dy dx to one side. And if it does, we're going to move it to the other side. So I'm going to move 3x squared and 3y to the left. And I'm going to move my 3x dy dx minus 3y squared dy dx to the right. Now you may be wondering, how do I combine the right side together? Well, to do that, I'm actually going to isolate my dy dx by factoring out a dy dx. So we get 3x minus 3y squared. On the left, I have 3x squared minus 3y. I'm going to divide both sides by this binomial, and then my dy dx will be isolated. So I've just written it on the right side instead, so that my dy dx is on the left. Now this may seem a little bit strange because we found dy dx, but in my right side, my formula, or my equation, it still has the y value. Now it's okay that it doesn't have the x all isolated by itself. As long as we know and we're given a point xy, we can still find the derivative. So for example, let's use this derivative, and I want you to find the points where the graph has a horizontal tangent. So remember that horizontal tangent means that my slope is 0. So for my slope to be 0, which is my dy dx, so remember that means that dy dx is equal to 0. All right, so I'm going to say that dy dx is equal to 0, which means that 3x squared minus 3y, all divided by 3x minus 3y squared, that has to equal 0. Now, since this equals 0, really I'm just concerned with the denominator. So we have 0 equals 3x squared minus 3y. And I'm going to move this to the side. So 3y equals 3x squared. So y is equal to x squared. All right, so the other thing, I'm going to bring back what I had before. And so my Folium of Descartes was x cubed plus y cubed equals 3xy. Okay, so I want to know, remember my question is find the points where the graph has a horizontal tangent. So I know that the horizontal tangent occurs when y is equal to x squared. So I'm going to go back to my original question, and I want to find out where those points are. So I'm going to take my x squared, and I'm going to plug it in where I see y. So I have x cubed plus x squared cubed equals 3x times x squared. So I have x cubed plus x to the 6 equals 3x cubed. Moving everything to one side, I have x6 minus 2x cubed equals 0. Factor out my x cubed, and I have another x cubed minus 2 equals 0. So I have two parts. Either this part equals 0 or the second piece equals 0. So if x cubed equals 0 or x cubed equals 2, so x equals 0 or x equals the cube root of 2. So plugging it back in to my original to find out what my y value is. So now I have my x values. I want to find out what my y value is. So x is equal to 0. Now I'm going to actually plug it into here because it's actually a lot quicker. I have y equals 0 squared. That means that y equals 0. So one of my points will be 0, 0. If x equals cube root of 2, I have y equals the cube root of 2, and then all squared. So my other point is the cube root of 2 and to the power of, or actually cube root of, actually let's make this to be cube root of 4. So if we go back and look at our graph, we have a point at 0, 0, and yes, you know, that is a horizontal tangent. And then my other point was at the cube root of 2, which is approximately here, I would say. And then, and you can check that that's actually the cube root of 4. And that's where the horizontal tangents are. Okay. All right, let's take a look at one more. So find the derivative of x squared plus y squared equals to 25, and evaluate that at the point 3, negative 4. Okay, so again, we take the derivative of x squared, and because it's with respect to x, that part will just be 2x. And then y squared will be 2y. But using the chain rule, because remember that y is, we're taking the derivative of y with respect to x. So we have to times that by dy dx. And then the derivative of 25 is equal to 0. Now it's sometimes nice to isolate the dy dx. So I'm going to go and do this. So dy dx is equal to negative x over y. And then when I want to solve this, I usually write this dy dx and then 3 comma negative 4 on the bottom. And when I plug in my point, I get negative 3 over negative 4, which means that this is going to be 3/4. Okay. Now one more thing I want to show you before we end is how do we find the second derivative implicitly? So we have 4x to the cube plus 4y to the cube, and because we're differentiating respect to y, remember this will be dy dx equals to 0. So I'm going to say this is dy dx, and let's isolate that. And then we have dy dx is equal to x cubed divided by y cubed, and this is negative. So now when I find the second derivative, so this is a little bit tricky, this will equal, now I'm going to differentiate this piece now. So we have to use the quotient rule. So the derivative of our numerator is going to be negative 3x squared times our denominator, not changed, and then minus our numerator. And notice it's negative, so I'm going to change this to positive x cubed times the derivative of our denominator, which is 3y squared. And remember, we have to take the derivative of y with respect to x, so this will be dy dx, all divided by y cubed, all squared. Now, remember that dy dx is actually this expression here. So I'm going to take this expression and I'm going to plug it in. So I have plus x cubed times 3y squared, and then negative x cubed over y cubed, and then all to the power of y to the 6. Now, to get rid of this fraction here, what I'm going to do is times the top and bottom by y cubed. So then I'm going to have negative 3x squared y to the 6, and then minus 3x to the 6 y squared, all divided by y to the 9. And we can simplify more by dividing by y squared.